Hello everybody, I hope you're all doing well. We're looking at question number 24 on the 2005 Cayley contest. So, the base of a rectangular piece of, a triangular, not rectangular, a base of a triangular piece of paper, ABC, is 12 centimeters long. The paper is folded down over the base with the crease DE parallel to the base of the paper. The area of the triangle that projects below the base, so I think the stuff below AB, is 16% of the area of the whole triangle ABC. The length of DE in centimeters is. Okay. So, 16%. What are we to do with that? Well, the area of the I'm going to draw a picture here. I think I can see where this one's going. But let's draw our triangle. So we go up ABC. Actually, no, it was C at the top, wasn't it? Because it was AB and then it was DE, yeah. AB and then C up here. And then we had, we'll give it a color. We'll have the blue crease line. And that was DE. And then it all gets folded down. And then we have this smaller red triangle here. Now I'm thinking we give names to some of these. So F, G, and H. Sure. Alright, now because they mentioned that DE is parallel to AB, I'm thinking there might be some similar triangles, some angles that are the same. So for example, I notice this angle C up here has got to be the same as this angle down here. And this angle here, X here, X here. It's got to be the same as X down here, and we'll put a little check. It's got to be the same as check down there. Opposite angles there, check. That's fine. Okay. So we can see that FGH, that downward hanging triangle, is similar, but not congruent, obviously, to, and let's make sure we get the triangles lined up right. So A is where the check is, F is where the check is. G is where the X is, B is where the X is, and then C is the common dot angle. Okay. So, but area of FGH is 0.16 or 16% of the area of ABC. So I've converted percents into decimals, but the reason I've done this is because these triangles are similar. Each length in FGH is some constant ratio R times the corresponding length in ABC. And if all your lengths are shrunk or stretched by the same amount, this affects area in a predictable way. I've mentioned this, I think, once or twice in past videos, but it's a nice geometric property that comes up. If you stretch all your lengths by R, your area gets stretched by R squared. Length is one-dimensional, so you stretch it by R to the 1. Area is two-dimensional, so you stretch by R to the 2. And if you had volume, which rarely happens, they don't do a whole lot of 3D on these problems, or on these contests, but the volume would then be stretched by R cubed, R to the 3, because volume is three-dimensional. Okay, so this is useful. I think it's going to help us break down this 0.16. So the lengths and thus, so the way you can sort of see it is if all the lengths, if we have a base and we have a height, if all the lengths are stretched or shrunk by the same thing, BR, then this guy here has 1/2 BH, and this one has 1/2 R squared BH. Okay. So that's just a nice way to try and to remember it, to draw the tiny little triangle. But this doesn't just work for triangles. If you had a pentagon that was, and all the sides were stretched by 2, the area would increase by a factor of 4. So the area is R squared times the area of ABC. So the area of FGH is R squared area of ABC. But we already know it's 1.6 times the area of ABC. R squared is 0.16. Now, if you were just doing this with percents, you'd say 16% and then R is 4%. And I think that's too much, because if you square root 0.16, it doesn't go to 0.04, it just goes to 0.4. So these side lengths are 40%. Now, we're after DE, and we're not especially close to DE yet. So can we do some more similar triangle stuff? Well, yeah. CDE is the same as CAB. Okay, so we see ABC is similar to DEC. Got to make sure the angles line up properly. So if we knew the similar sort of R that DE is stretched by, well, we know AB is 12, so we just do 12 times 0.6 or something. Or 0.8 or 0.7, or it might even be something really weird like 0.75. Who knows? But we can try and work that out. Okay? Because I think I'm just going to put a little dashed line of where FG was. So we know this is 0.4 times 12. We know that length. That's not so bad. And I suppose we could add in the height and these lengths. We don't actually know what any of them are. But since they're parallel, yeah, so this will work. Since they're parallel, we get right angles here. But we took CDE and folded it over. So this height here, the height between DE and FG, is the same as the height between DE and AB. So let H be height of ABC, and I don't know, D be the distance between DE and AB. I don't know if we need D, but H is going to be 2 times this D plus, and then 0.4 times H. So if we bring the 0.4 over to this side, we get 0.6H is 2D. D is 0.3 times H. Okay. I think I need a bit more space, but if I redraw this again with this new information, I think we've got it. A, B, C, because all we need to know is the ratio of DEC to ABC. So we had 0.4, and then we had another 0.3. So the height of DEC is 0.7h. So 0.7 is ratio of sides between DEC and ABC. So DE is 0.7 times AB, which is 0.7 times 12, which is 8.4. I can do that exactly in my head, but of course, if you need a calculator, no shame in using your calculator. But 12 times 7 is 84. I've seen that a lot. And we just shift the decimal over. So 8.4, is that one of the... Yeah, it's B. So there we go. So that leaves us a little bit of space, but I have a feeling question 25 is going to take a bit more than a little bit of space. So we'll flip the page in anticipation of our very last question, question 25. Join me for that one in the next video, and in the meantime, have yourselves a wonderful day.